our discussion of the continuous time case. So, in order to find an impulse representation for continuous signals, continuous time we first need to find out how to go about it. Let us try a crude approach. The crude approach would be to get a very coarse representation instead of an accurate representation, a very coarse approximate representation for a continuous time signal to begin with. So, in order to do this, let us first take some continuous time signal, a graph of a continuous time signal, and see what we can do with it. So, here goes. This is the time axis, and on this let us sketch some continuous time signal x l. Let this be x t. Now, we want a representation for this. The first thing I will try to do is to form what I call a staircase approximation for x t. Let us call this signal x hat t. The idea of a staircase representation or a staircase approximation is that x hat t does not try to be equal to x t at every point t. Instead, at periodic intervals, at periodic instants of time, namely t equal to 0, t equal to delta, t equal to 2 delta, and so on, x hat t will be equal to x t. At other points between these points of equality, x hat t will be constant at the most recent value. So, in order to do this, let me first mark out on the time axis. This is the time axis. On the time axis, let me just mark out first the points delta, 2 delta, and so on. We will also have, of course, minus delta, minus 2 delta, and so on. Now, let us start. What does this x hat t do? At minus 2 delta, x hat t will try to match x t exactly. So, at t equal to minus 2 delta, this will be a point on x hat t. What is its value at minus delta? Its value at minus delta again has to be equal to x t. In between these 2 points, x hat t should remain constant at the value it found at x at t equal to minus 2 delta. So, it stays constant in between these 2 points. Now, at t equal to 0, x hat t will have to take the value of x of 0, x hat of 0 has to be equal to x of 0, but between t equal to minus delta and t equal to 0, it will stay put at the value x hat of minus delta or x of minus delta, and so it will remain constant like this. Next, at t equal to delta we have this value, and from there up to this point it will have this value. Likewise, if I go on doing this, I would get the this is the staircase. Just for psychological convenience, I will have risers for the staircase as well. I will connect these parts of the staircase by vertical lines, knowing fully well that that is frowned upon by the purist. So, this red function is the staircase approximation x hat t of x t. Now, because it has discretized the continuous time using a unit that we have called delta, I will actually call this x hat subscript delta of t. And what can I say about the value of x hat delta of t? I can say the following: x hat delta of t equals x of t at t equal to n delta at other points. Its value will be equal to the most recent value of x t, most recent sampled value of x t. So, thus x hat at delta by 2 will be equal to x of 0, x hat at 3.2 delta will be equal to x of 3, and so on. So, we have this. Pause. And at points not equal to n delta, at points of time t not equal to n delta, we will get x hat delta of t equals x of delta times the floor of t by delta, as we have written over here. This completely describes the staircase approximation in terms of the original signal. It is clearly an approximation. Now, the important things to recognize about this approximation is that as we make delta very small, x hat delta of t will closely resemble x t more and more. So, though at present and in the kind of sketches we have drawn, x hat delta looks very crude, x hat delta of t looks very crude compared to the original signal. This can be improved if we only make delta smaller and smaller, but that is a separate issue. Right now, suppose we are prepared to accept x hat delta in lieu of x t, x hat delta of t in lieu of x t as the signal that we want to study. Then can we find something like an impulse representation for x hat delta of t? The nice thing about x hat delta of t is that it has only finitely many different values within a finite interval of the time axis. If we go back to the earlier figure, we find that in this interval of the time axis from -2 delta to approximately 4 delta, we have 1, 2, 3, 4 5, 6 different values of x hat delta of t, unlike the original x t which had an infinite number of different values in this same interval. So, in some sense we have reduced the problem of continuous time signal representation to something that resembles the discrete time signal representation. So, let us say if we are asked to represent x hat delta of t in using impulses, represent x hat delta of t instead of x t in terms of impulses. We still do not know what we mean by impulses, but let us see. How would we go about it? We would try to define a suitable impulse. Impulse signal. In this case, it turns out to be convenient to define that signal as a function sketched here. This is what I will call, for lack of a better name, I will call delta subscript capital delta of t. This is the time axis. This signal will have a non-zero support, that is a support from 0 to delta. It is 0 outside this interval, and within this interval it is constant and takes on a value equal to 1 by delta. Fine. This is what I call delta delta of t. I will call this now, for again lack of a better name, I will call it the approximate impulse. Delta delta of t is called the approximate impulse. Can I use delta delta of t to represent x delta of t? X hat delta of t. The answer is yes, and we could do it by decomposing x hat delta of t into x hat delta k of t, as we did last time. Each of these x hat delta k of t would be non-zero only in the interval k delta to k plus 1 delta, and in this interval it would take the value of x t at t equal to k delta, that is, it would be equal to x of k delta, and it would be constant in that interval. At all other points of time it would be 0. So, suppose we had x t as we had taken earlier, then here is our x hat delta of t. Now, I will represent this as a sum of shifted and scaled approximate impulses But before I do that, I will first express it as a sum of simpler functions. These simpler functions would be like this. This is minus delta, 0, delta, 2 delta, so on. I have this. So, I would express this as a sum of the following signals. In this place, I would just have one pulse like this. This I will call x minus 1 delta of t. Then I would have the next function x 0 delta of t, then the next function x 2 delta of t, sorry, x 1 delta of t, then the next member would be 0 up to here and then be negative this would be x 2 delta of t. So, if you added x 1 delta of t and x 2 delta of t plus x 3 delta of t plus so on, you would get x hat delta of t. So, we can write x hat delta of t equals summation x k delta of t for different k's. Fine. So far so good. We seem to have completely sidetracked the original problem of finding a representation for x t. We have now become completely preoccupied with finding a representation for x hat delta of t. We have set our sights a little lower. We have recognized that handling x t directly would be biting off more than we can chew, and so we have bitten off only x hat delta of t for the time being, and we want to represent this. That representation can be made in the following manner. Now, each x k delta of t can now be represented in terms of the functions delta delta of t. How would we do it? Shift them and scale them and add them appropriately. The game is very similar to what was done in the discrete time case. Let us first try to characterize x k delta of t. What can we say about x k delta of t? X k delta of t equals 0 for t less than k delta it is also equal to 0 for t greater than equal to k plus 1 delta. It is non-zero only between these 2 points. And what value is it between these 2 points? It is equal to x, the original signal x at k delta in the interval k delta less than t less than equal to t less than k plus 1 delta. This is our characterization of x k delta of t. Contrast this with our characterization of delta delta of t shifted to the point k delta. So, we want delta delta of t minus k delta. Delta delta of t minus k delta equals 0, t less than k delta, 0, t greater than equal to k plus 1 delta, and it is equal to 1 by delta in the interval k delta less than equal to t less than k plus 1 delta. So, this is delta delta t minus k delta, that is the delta delta signal, the approximate impulse shifted to the point t equal to k delta, and this is the component of the staircase approximation, the kth component of the staircase approximation x hat delta of t. This kth component is what we have called x k delta of t. So, you will see that both x k delta of t and delta delta of t minus k delta are constant in the interval from k delta to k plus 1 delta. One of them is equal to x of k delta, the other is equal to 1 by delta. So, all we need to do is to find the appropriate scale factor, and we would have to begin with a means of representing the different component, simpler component signals x k delta in terms of the approximate impulse. So, let us do this now. क्या हुआ? हो गया? बस नमस्ते आज के लिए.
आपने so that करके कंटिन्यू करने को किया तो मैंने कहा टेप बदल हो जाते सारा.
We have x k delta of t in the region of our interest. This is equal to x of k delta, and we have delta delta of t minus k delta, assuming a value equal to 1 by delta. Both these in the region k delta less than t less than equal to t less than k plus 1 delta. So, clearly by comparing these two, and both these functions are 0 outside this interval of k delta to k plus 1 delta. So, in order to make delta delta of t, or in order to express x k delta of t in terms of delta delta of t minus k delta, all we have to do is scale delta delta of t by x k delta of t, which is x of k delta. We can therefore write that x k delta of t equals x of k delta 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 t minus k delta. This is almost okay, except for this one deficiency, that delta delta of t minus k delta has an amplitude of 1 by delta, not of unity. Therefore, we have to further multiply this by delta. This gives us the expression for x k delta of t in terms of our approximate impulse delta delta of t minus k delta, the shifted scaled approximate impulse. This is the equivalent to our earlier expression, where we had x k of n in terms of delta n minus k times x of k. So, with this in hand, it is very simple to see what we do next. Remember that our original exercise is to represent x t, but our intermediate exercise is to represent x hat delta of t, which is the staircase approximation of x t. So, the staircase approximation is what we will now construct using shifted and scaled approximate impulses. For all k, that is k running from minus infinity to infinity, this is what we know is valid, and now with our new information we can express this as k equals minus infinity to infinity x k delta 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 t minus k delta times delta. So, this is the expression we were looking for. If our exercise was only to represent the staircase approximation, then we have already achieved our objectives. We have now a means of representing x hat delta of t in terms of shifted and scaled approximate impulses, but we have still got some distance to go from here, because we actually want to express x t in terms of x hat delta of t. So, x hat delta of t is not good enough. We will have to see how to make x hat delta of t become close to or equal to x of t, and that is reasonably easy to see. It is evident that as this discretization size delta, discretization unit delta tends to 0, x hat delta of t will become more and more close to x of t. Thus, we can write that the limit as delta tends to 0 of x hat delta of t equals x t. Now, when we do this, we will have a larger and larger number of the component signals x k delta of t, because in any given interval we will have a larger number of units as delta tends to 0, because delta is the unit. Thus, we will have a more and more crowded representation. Let us try to make a diagrammatic exhibition of this fact. Suppose this is x and originally delta is this big, delta, 2 delta, 3 delta, minus delta. Then the first staircase approximation would be like this. Cut. We have sketched here the same signal x t in black, then there is a signal sketched in blue, in red, and that is x delta of t. There is a third signal sketched in blue, which is x delta prime of t, we have chosen delta prime to be equal to delta by 2 half delta, and we can see from the horizontal time axis what relationship delta prime bears to delta. We can see that delta prime is half of delta. We have marked 3 delta, 5 delta, 3 delta prime, 5 delta prime here in this axis, and we have constructed these two staircase approximations, x delta prime of t and x delta of t. X delta of t is seen to be more distanced from x of t than x delta prime of t, and this is achieved simply because x delta prime of t checks the values of x t at every time k delta prime, which is a smaller time interval than k delta. Thus, it is evident that as delta tends to 0, x delta of t will tend, x delta hat of t will tend to x t. So, let us see what this entails. If we wish to make x hat delta of t tend to x of t, then delta must tend to 0. Let us see the consequences of delta tending to 0. If we want every step of our derivation made until now to be valid, then we should make appropriate definitions for the approximate impulse. The approximate impulse was earlier defined as delta delta of t. Now, this approximate impulse is going to undergo modifications of a suitable kind when capital delta, the discretization step size, tends to 0. Thus, for example, if we make a few versions of delta delta of t for varying values of delta, we would get a diagram like this. For large delta, we would get something like this, and we would say that this is, let us say, delta 1. If this is delta 1, then this is 1 by delta 1, and we have this diagram. So, this is one choice of delta, in which case this function that we have just drawn will be what you can call delta delta 1 of t. If we make delta smaller, let us make delta 2, that is half the size of delta 1. Then the height of this new function in its non-zero region, in its support, must be equal to 1 by delta 2, which is therefore twice of 1 by delta 1. So, we get a new function that has this shape. This is delta 2, and what we just have drawn is delta delta 2 of t. We could make a third one if we liked, which had an even smaller support, say delta 3, then we would have an even taller function, because 1 by delta 3 would be even smaller than 1 by delta 1, or 1 by would be even larger than 1 by delta 1 or 1 by delta 2. We would get, this is not actually drawn to scale, but this would be 1 by delta, ought to be 1 by delta 3, and what we had just drawn earlier is 1 by delta 2. So, if we remain consistent with the way we have defined our approximate impulse, then it turns out that as the discretization step gets smaller and smaller, these approximate impulses get narrower in time and taller in amplitude. and it undergoes these two changes in a very systematic manner, and that systematic fact is that if its width is delta, then its amplitude is 1 by delta. So, that the area under delta delta of t is constant and equals unity. So, we have to maintain the area of delta delta of t to be 0 as the discretization step is made smaller and smaller. So, finally, the question of how small do we need to make delta? The answer unfortunately is that no finite size is small enough, because we want to approximate a continuous time function x t, and a continuous time function uses time as a real variable. Now, a real variable, the real line, is infinitely divisible. So, theoretically x of t can vary from instant to instant. You can take as small an interval of x t as you like and still observe variation in it. So, if we want x hat delta of t to be faithful to x of t at whatever level of magnification we wish to observe x delta of t in, then it is imperative that delta must actually go all the way to 0. Only then can we hope that the staircase approximation x hat delta of t will become actually equal to x of t. So, this is what we have to aim for. Now, let us see what happens to the approximate impulse as the unit of the discretization goes to 0. The area, as we said, must remain fixed at unity. The width of the support gets smaller and smaller and tends to 0. If both these constraints have to be met, then necessarily the amplitude 1 by delta should tend to infinity. So, as delta tends to 0, one by delta will tend to infinity. There is no help for it. So, what do we have in the limit? What we have in the limit is a very awkward mathematical entity. It has, in many ways, it lacks the basic properties of a function, because a function, as we have understood till now, is a map from the reals, that is from the time axis, into the range which we expect to be the set of complex numbers, and every complex number in the set of complex numbers is finite. However, 1 by delta, as we observe here, is infinite. Okay? So, while every complex number is finite, and therefore, every function must necessarily have a finite value at each point of time delta delta of t will not satisfy this as t tends to infinity, as delta tends to 0. So, delta delta of t, the limit as delta tends to 0 of delta delta of t will tend to infinity at t equal to 0. This is a paradoxical situation, and this is why delta delta of t in the limit, which we call, in fact we have a name for it, we simply call it delta of t. We define the limit of this sequence of functions delta delta of t as capital delta tends to 0 as an object that we call delta of t. So, let us see what delta of t, what we can say about delta of t. Delta of t is the limit of the sequence of delta delta of t's, and hence delta of t equals 0, t not equal to 0. This much we can say, because this is a common property of all the delta delta of t's outside their support, and the support of delta of t, which is the limit of that sequence, is indeed 0. The width of the support of delta of t is actually 0. So, there is no problem, it will be 0 for all t not equal to 0. Now, what value will it have at t equal to 0? We can't answer this question, because the value it will take is not within the set of complex numbers. Infinity is not within the set, and this value that it tends to take will be very, very large. However, we can cease to discuss the property, this particular property of what value it takes at t equal to 0, and instead focus on more secure things, things we are more comfortable with, things that we are more confident about. One thing we are very confident about of delta of t is the area under the curve. The area under delta of t must be the same as the area under every member of the sequence, because we have set that area to be constant and equal to unity. Thus, we can say that the area evaluated of delta of t dt equals 1, and since its value is 0 for all t not equal to 0, we could take any interval containing 0 and integrate delta t over that interval, we would still get 0. In short, this is equal to integral from any minus a to a, where a is greater than 0, delta of t dt. This is the same, it will have a area of unity. Fine. This delta of t is now called the impulse, simply called the impulse, because it is no longer approximate, it is the ultimate impulse. It is what we were hoping to construct. Impulse for continuous time signals is just called the continuous time impulse. It is also called the Dirac delta. So, all that we have said on this panel is the only statements that we can make with certainty about the Dirac delta. Some things we can say is that the Dirac delta is not a function, because it is not possessed of values within the set of complex numbers for all time, in particular at t equal to 0, where the value that the Dirac delta takes does not lie in the set of complex numbers. So, it is not a function, it is an entity, that is all we will say it is right now, with this property that the area under that entity, in the normal way we define the area under any function, evaluates to 1, and it will evaluate to 1 if that integral is carried out over any interval that contains t equal to 0. We can also say with certainty that delta of t is 0 for all points of time not equal to 0. So, this much we have said. There is one more important property that delta of t will have. Remember that in our process, in our exercise of coming to delta of t, we have gone through the representation of x k delta of t. And we said that x k delta of t is just equal to delta delta of t minus k delta times x of k delta times delta. So, if we extend this property all the way until delta tends to 0, what will we get? We have essentially here multiplied the value of x t at t equal to k delta. We have multiplied that with the approximate impulse and scaled it by delta, and this gives us the value of x t at t equal to k delta. So, as we make delta tend to 0, delta delta of t has now become delta of t, the exact impulse or the ultimate impulse, and delta of t will still be used to sample the value of x t, not in gross intervals of width delta, but at a particular point. In short, there is something called the sifting property. Of the Dirac delta. The sifting property of the Dirac delta is simply this: if I try to take any function x t, multiply it with a shifted Dirac delta located at some t naught, that is delta of t minus t naught, and evaluate this product, the integral of this product over any interval of time that includes the point of occurrence of the impulse, which is now t naught, say t naught minus epsilon to t naught plus epsilon, where epsilon is of course greater than 0, then this will be equal to x of t naught. It is this property that was that we sought when we wanted an impulse representation for continuous time signals. In the discrete case, we wrote that x k delta n minus k, or rather x n into delta n minus k, just one second. X n times delta n minus k was equal to x k. That is the equivalent property we want here. There we were able to sample the value of the function, discrete function x n, discrete time function x n at the point k by multiplying it with x delta n minus k. which is the shifted discrete Kronecker impulse at n equal to k. Here we have the Dirac impulse located at t equal to t naught, and we wish to evaluate x t naught. We wish to express the number x t naught using the shifted Dirac impulse to sample x t. So, we have this. So, in general we can always write the shifting property as integral minus infinity to infinity. We can always use a larger interval because the Dirac impulse is anyway 0 for any point outside the point of its occurrence, x t delta t minus t naught dt equals x t naught. This completes our impulse representation. For continuous time signals. So, we have an impulse representation. Now, what do we do next? We have to carry out the same set of steps that we used in order to obtain the convolution of discrete time signals. We apply homogeneity, we apply time invariance, then we apply the property of linearity of the systems in question, and then we find that y t, the output of a continuous time system, which has been impressed with an input x t, may be computed using something that is also called the impulse response here of the continuous time system.